I'll be talking about how we've been using VSim to model wafer etching problems and plasma processing more generally. Just as a quick introduction, so there I am, and yeah, I've been here for about 1.5 years. I've been using particle and cell as a modeling tool for many years, for about 15 years. But there are many uses for it. And so I'm still coming up to speed on all those uses, or many of them. So let's go ahead and get started. Okay, so let me just give a brief background to this problem. In this particular problem, we placed a silicon wafer in the simulation domain. And the dimensions of this would be it's about 10 to 20 centimeters in diameter, and it's a few millimeters thick. A plasma is generated, which reacts with the wafer, which then etches a desired pattern on the wafer. So VSim, how can VSim be used for this? So we can model many of the reactions which occur in the plasma and at the plasma wafer interface. We can put dielectrics into the simulation to determine how to create a uniform sheath across the wafer. So a desired outcome for this sort of problem would be how to create a uniform sheath across the length of the wafer so that the ions impact uniformly. So just again, an overview of what is VSim. VSim is the entire computational engine, the visualization setup, the post-processing, and the data visualization package. For those of you who've been using this long enough, you may recall the term Vorpal. That would be the computational engine. So VSim is a multiphysics, fully kinetic, electromagnetic particle and cell software. By multiphysics, the core algorithms are a plasma modeling tool with many associated physics, such as reactions with neutrals, secondary emissions, and other processes. Fully kinetic means we can capture nearly all plasma processes. I say nearly all. There are things that are just impractical with PIC, or where the actual assumptions break down. But VSim can tackle a large body of problems. And by electromagnetic, I mean Maxwell's equations are solved at each time step, and the plasma current and charge density are used as source terms, along with the addition of boundary conditions and external source terms. All right, so let's go ahead and move on. So what would be the advantages of using VSim for this problem? We are solving the electric field fully self-consistently. So in these simulations, these are electrostatic. So we're not solving for the magnetic field because it really doesn't play a big part. At least the self-consistent magnetic field does not. Now the second bullet point here is a big one. This sheath electric field is directly responsible for accelerating the ions into the wafer. So what we care about for this problem are the ions, but the electrons play a very important role for figuring out the electric field, and in particular, getting the sheath dynamics correct. So when a plasma interacts with any surface, including the wafer, a sheath naturally forms, and we'll see in a movie in a few minutes that this sheath oscillates between about 10 to about 100 Debye lengths, depending on where you are in the RF cycle. Therefore, it's essential to resolve the Debye length to get that electric field correct. And so this presents a real challenge for how to do this. You can't use too big of a time step or too big of a spatial step, or else you just won't get that Debye length resolved correctly. And then this fourth bullet point is really sort of hitting the nail on the head, because VSim captures all of these sheath dynamics naturally. A PIC code just does this. You don't have to do anything. It just gets it already. So there's no ad hoc methods that are needed, which would be needed in any fluid code. For example, you'd have to make sure all the terms are in there. And so in my opinion, any fluid model is just going to be sort of an ad hoc way of doing it. And it may end up getting it right, but it's going to be through a lot of trial and error that we just simply don't have to do. And finally, VSim includes many collisional processes and secondary electron emission processes. All right, so here's an overview of the setup. So in this simulation, I've got this silicon wafer, and I've got a focus ring, and I can easily adjust both of them. For example, this height here can be adjusted very easily. Now, with our modeling method, what we've done is, because this is a very computationally intensive problem, we are not, a realistic chamber may extend, much further out. And so what we're doing is we're capturing in this simulation domain, we're going far enough into the bulk of the plasma that we're away from the sheath dynamics, because we don't want any interference there. And then we have been able to figure out how to input and inject the plasma species correctly, and I'll go over that in just a minute, and also get the Dirichlet boundary condition correct. That's where you specify the potential. All the simulations are done in a 2D cylindrical coordinate system. So this is the R-axis here, and this is the Z-axis. And so let me just show you a movie of some results. So I'll camp out here for a minute. I rotated the whole thing for this presentation. And so here's the wafer, here's the focus ring. And just as a bit of background for the non-specialists, a focus ring is put in oftentimes a very complex geometry in an attempt to shape that electric field near the edge. Because what happens is that without a focus ring, because of this edge right here in the wafer, let me go back here, because of this edge right here, you end up getting edge effects that modify the electric field that end up messing up the ions. And therefore, traditionally, they've only used a part of the wafer where there's a really uniform electric field for the microelectronics device. And so the goal here is to make that, extend that uniform electric field to the edge so that they can use all of the wafer. Okay, so these two boundaries are Neumann. That allows the potential to float, which you can see it here, it's floating. We put a time-dependent potential modeled from other capacitively coupled results up here. And then there's an RF source down here. So we did have to figure out how to get this plasma potential correct in order to get a good simulation. And we've done that for this problem. Now, the particles are injected with a flux-conserving particle injection. And I'll get into that in a little bit. Over on the left and the right boundaries, I'm reflecting particles. And then the particles are absorbed on the wafer and the focus ring. And that gets put into the electric field calculation. In some simulations that I'll show you, I've also emitted secondary electrons just to see what that effect would be on the ion angular and energy distribution function. So let's go ahead and just briefly play this movie. You can see, let me just pause it, right here. This would be the sheath region here. And you can see that sheath region is oscillating it oscillates with the same frequency as the external RF source. The ions are injected up here, and they are accelerated down. And there's a color scale for the electrons that gradually goes from white to black. And you can see there's very little acceleration in this region in the bulk of the plasma, and most of the acceleration occurs in the sheath region. So there's a question: what is the trade-off between a focus ring and axial static magnetic field to do the same task? I have never played with any sort of external magnetic field for these, so I don't know what the answer to that question would be. I simply don't. I'm wondering if it's just more pragmatic to put in sort of dielectrics than try to play around with shaping a magnetic field. That might be one trade-off there, just sort of a practical from the standpoint of manufacturing. Okay, so this keeps restarting, but at any rate, this is just sort of this oscillating that you see throughout the whole cycle here. So I'll go ahead and move on. Okay, so just a more explanation of the simulation, the setup. The simulation domain includes the near wafer region. Okay, so I've already gone over this. So I guess the final point, though, is how do we specify? So VSim has a nice emission boundary condition, which places the particles correctly in boundary cells. So the question then is, how do you specify the velocity correctly? So we've injected particles at that top boundary to model a small part of a much larger plasma. So if the particle injection is done correctly, sorry, this should be incorrectly. If the particle injection is not done correctly, a sheath will build up, an artificial sheath, because in the real setup, there would be no sheath there. So we found a way to eliminate the sheath. In other words, we found the correct way to do this. So we'll show that density, flux, and temperature are conserved. And of course, we'll show that no sheath forms at that upper boundary. So the injection method that we've used, the simulation is initialized with a distribution function. It's given by f of v, which we've just done using a Maxwellian. We assume that this is a drifting Maxwellian towards the wafer with no drift in the other directions. Plasma is initially charge neutral with no current density either. So the two drifts for the two species are the same. And just sort of in a brief overview of the theory. David Bohm, a big name in physics in general, came up with this criteria that if we inject the species at the ion sound speed, that there should be no sheath. So we've chosen the drift speed to correspond with the ion sound speed, which would be very slow. So another question here. I can, okay, so Sudhakar, the color scale, let me just briefly go back to that. The color scale is for the potential. So this, sorry, I didn't mention that. This background color scale is the potential. And it extends from -300 to 0 volts. Robert asked, how well does a simulation sheath, pre-sheath structure agree with analytic or fluid? We haven't done any quantitative predictions with fluid models, and so I don't actually know. That would be definitely a good project to work on, a more quantitative comparison. I mean, I've read through some of the papers that have done this, and we get qualitatively good agreement, but I've never worked with any of those folks to get their data to do a more quantitative comparison. Okay, so back to this initialization method. So again, we've injected these particles with the ion sound speed. And let me just give you a brief overview of how a particle, the initial particle of each species, is chosen in a pick code. So the way it's done is that you choose a random number R, you set it equal to this quantity on the right. And the key here is to invert this on the right and figure out what V sub x is. And then if it's a Maxwellian, the nice thing about this is that you can solve this analytically, which speeds up the initialization. And this same inversion method can be used for injection as well. But the tricky part is if you inject with a strict Maxwellian, then what happens is that you get these particles that move away from the boundaries faster if they're for the high energy particles compared with these low energy particles. So if you use the Maxwellian to inject, what happens is that you inject too many cold particles, which is what I'm showing you here. So the proper way is to inject not with F of V, but V times F of V. And if you do that, then you get the correct injection. And so here's an example of phase space in which, so again, so I went over this slide. So I'm going over these very quickly here. So this is position versus velocity. So this is a plot of phase space. And then this color scale is also a plot of phase space. I just bin the data to get a histogram. And so this is Vx versus x. And what you're seeing is that if I inject with the Maxwellian, I'm getting too many particles, too many cold particles injected. But if I inject with V times F of V, again, this is phase space, V versus X, then this is the initial phase space, and this is phase space at some later time, then I'm getting the correct injection. So you don't see an over-injection of the cold particles. So the tricky part then is how do you invert that interval that I showed you before? There are ways to do it, but there are other ways than what we did here, but this was just one way that we came up with. So again, what we need to do is invert the right-hand side so that I can solve for the velocity. This can be, again, this can be inverted analytically, but if it's drifting, it cannot. So the way that we did this was what's called rejection sampling theory. I'm not going to go through the details of this method. I'm more than happy to send you these slides and you can go through it. But we've implemented this method in a Python script, which we call using a space-time Python function in VSim. So I'm just going to skip a few of these slides here and just show you the result. So this was just, let's see, the orange curve is an analytic distribution function, analytic V times F of V, where F of V is a Maxwellian. I set V drift equal to V thermal in this example, and then I use rejection sampling theory to determine the particles that fit within this distribution function, and the numerical result is this blue curve. So we get very good agreement with an analytic method. And we've implemented this in VSim. So this was a very nice approach, a very nice way of injecting the particles correctly. And it was very easy to implement in VSim. I just wrote up this script and this function in a Python script, and VSim calls it automatically. Okay. Okay, so if electron temperature is high, the thermal velocity may be higher than the drift. Yeah, I mean, this method works regardless. This is a general method. The only thing I'll say is if the V drift is very high, much higher than the thermal, then this is kind of overkill because the distribution function almost looks Maxwellian. You can tell that I'm multiplying this by V times F of V here, but if V drift is very large, then you don't really need to use this method. But here, V drift is actually much smaller than the thermal velocity. So this method is required to get the V times F of V correct. So for these simulations, so now that's just sort of a brief introduction of how we came up with our particle injection method. And the advantages of this method is we don't have to simulate the entire simulation domain, and we can really concentrate on the sheath, which is what the essential physics is here. I just set the electron temperature to 3 eV, the ion temperature to 1. I just played around a little bit with the drift velocity. Anything around the sound speed gave us good results. For some simulations, I've included an argon neutral background just to demonstrate the role of collisional processes on the ion and angular energy distribution function. For those simulations, the temperature was 0.15 torr. And then I did a fourth simulation where I included secondary emission off of the dielectric. So let me go over the angular energy distribution function. I've written a post-processor to do that, and I'll show you how to use that. That can be done within VSim. So I'm comparing, so basically what I'm doing is I'm binning in angular and energy space. And there's a nice history that can be utilized in VSim that allows for very nice post-processing. And I'll be comparing the ion angular energy distribution with different focus ring heights, with the presence of secondary electrons, and also collisional processes. So I sort of did some case studies. And then these are the collisions I included. I included ionization, elastic, and I included one excitation collision, the one with the largest cross-section. For the secondary emission model, basically, I broke up the ions and electrons into two parts. So one part would accumulate on the surface, and then the other part, like if an ion hit it or an electron hit the dielectric, it could give off a secondary electron. Now, VSim has lots of ways of modeling secondary effects. It's a very complex process, and I took the simplest approach for this example. And you could do lots and lots on your end to put in more complex secondary emission models. So let me now get into the results. So my first study was, I just compared the two different simulations with two different focus ring heights. So this is the focus ring here, and you can tell on the right that the focus ring is lower. This is after about 14 RF cycles. And we'll look quantitatively at how this impacts the sheath, but we'll need some cutouts. And I did everything, a lot of this data analysis I did in Visit, which you can call directly from VSim to get more flexibility. All right, so here's a cutout. It's along this line, this black line. So I tried to go through the sheath. In this case, it went through the focus ring as well, but that doesn't matter because what we care about is what happens at the very end of the wafer. So this was with a high focus ring, the black curve, and the blue curve is with the low focus ring. This is potential. Let me go back to this plot. So this is potential. So the color scale is potential in volts. It extends in both cases from -400 to -20 volts. So the color scale is the same on both axes, or I'm sorry, on both plots. And then this plot here is just a cutout. So this here is the vertical scale is the potential in volts. It extends from about -400 to approximately -300 volts. The blue curve is a cutout with the low focused ring. The black curve is a cutout with the high focused ring. And I think you can tell that there is a much more uniform potential with the lower focus ring. And so that's now the edge of the wafer is right here. So this black vertical line is the edge of the wafer. Now, we can also compare the angular energy distribution. And so let me briefly describe what's required to use that analyzer, because you can't use the analyzer unless you get the data, unless you collect the correct data. So you need to collect, this is the data you need to collect. So let me go back actually real briefly to this picture. Actually, yeah, so this is the wafer right here. And what happens is that when an ion hits that wafer, for every single ion that hits that wafer and every single time step, it collects this data, which I'm about to show you. So it collects the position. Of course, you know the position along Z, it's hit the wafer, but it still collects it. And then it collects the position along R, the position along the wafer. It collects all three velocity components, the energy, the weight of the particle, the charge, the time the particle hits, which is important, very important, and then the number of particles in the macro particle. The analyzer then bins this data along the surface and in time. So you could say, okay, I only want to look at the data, the particles that hit between RF cycle 11 and 12. It'll bin that. It'll only look at that data. I only want to look at the data at the very edge, for example. It'll bin that data. And then it takes the particles that are within, some region of the wafer in some time interval, and it further bins the data as using a 2D histogram function in Python as a function of angle and energy. And all of this can be done in VSim. So here's a snapshot of the analyzer. Let me actually pull it up in VSim, so you get what it looks like. Species name, ions, the start time and the end time, and that's based on the RF cycle. If you try to go outside of the simulation, you'll get an error that says you didn't collect data up to RF cycle 18, for example, if you tried to do that. Lower position and upper position. So I've been looking at data at the end of the wafer. So this is in meters. The name of the history. So for that, let me go back and show you this history. So in the visualization window, if I right click here, I go to add log history, and the actual history is called absorbed particle log. I already created one, and I called it left ion loss. If I click here, I can add a particle quantity. Say I want to add position. Then I can add position 0, position 1, and this is just a 2D simulation. So you'd want to just do position 0 and position 1. And so that's what these are, position 0 and position 1. And so that's how you would use this history. So there's lots of particle information you can store with this log. And that history was called left ion loss. And then this is information that you need for binning the data. So you need the bin in time and position. And now you need to put in information for creating the histogram. So number of energy and angle bins, lower and upper energy, the lower and upper angle that you want, the angular frequency of your RF source. This information here is used to figure out the time to bin the data. So if you had multiple RF sources, for example, with different frequencies, just pick one. And then that will be used as your reference for your start and end time. This is a two-dimensional simulation, and the perpendicular direction is in the positive x direction. Okay. So that's a brief overview of that history. Or I'm sorry, this analyzer, which will be coming out with VSim-11. And then this is the result of the high focus ring. So this is angle energy here on the horizontal scale, and this is angle on the vertical scale. My apologies. This is energy on the vertical scale, angle on the horizontal scale. Now I can integrate over all angles and all energies to get 1D plots, and that also comes with the analyzer. So let me show you what that looks like when you actually pull the data up. So if you run this analyzer, it'll create a data set that then is read in the visualization window. And that data shows up as 1D field data for the line plots. And then for the colors, for the plot, for the data, plot as a function of energy and angle, that shows up as a 2D under the fields analysis here. Okay, so let me open up a new window just so you can see how to do that. If you open up a field analysis window, click on field, and then this was called ions, angular energy distribution. Of course, you could do the same analysis for the electrons, but you'd have to collect that history data when you ran the simulation. So if I click there, then it gets pulled up here. Okay. So now this is just the same data that you saw over in VSim, and this is what it looks like. These are 1D plus. Now this is the ion energy distribution. So this axis here is energy, and this axis here is angle. And then what you see is a asymmetry here with the high focus ring. And so this would not be a desired result. We want a symmetric, we want the ions to impact uniformly into the wafer. So I ran another simulation with the lower focus ring. And then this is what the ion angular energy distribution function looks like with the low focus ring. Again, this is energy versus angle. And then this is what this looks like here. I plotted the data on top of each other. So this is, well, before I get to that, this was ion angular distribution here and energy down here. And we now see that the ions impact more uniformly. And then I plotted them on top of each other. The low focus ring is, I guess, the green, and the high focus ring is the black. So my conclusion here is clearly there's an optimal height for the focus ring, and you could use VSim to model that to, you know, especially with much more complex geometries, dielectrics that you include. So one of the things that I see, obviously, is nothing's really coming in at 0 degrees, or exactly 0. It's close. You know, this is a few degrees here. So I've added these collisions, impact, ionization, excitation, elastic, background neutral density, pressure is 0.15 torr, but you could put in arbitrary densities. As you go up to higher densities, up to about an atmosphere, it gets very computationally intensive, which you saw yesterday when I did that corona discharge. But my understanding is the densities don't really approach an atmosphere. But that's, I suppose, very problem dependent. Remember that your grid size needs to be less than your mean free path. Your collision time, your time step needs to be less than the collision period. That's all very easy to do with smaller pressures. Finally, I'll note that if collisions result in lots of new particles, it's useful to use managed weights, because as you add new plasma particles, your simulation will get bogged down. And so I didn't use managed weights because I didn't find that to be a problem, but it is a very powerful part of VSim. And I can help you set that up if that's what you're interested in. My analyzer still does work with managed weights because I am collecting the particle weight, which gets put into the histogram, the binning in Python. Okay, so now let's just compare runs with and without collisions. So this is potential. Again, this is a cut along the sheath. I'm using the low focus ring because I was getting better results with the low focus ring. And the black curve is with collisions. The green curve is without collisions. These look very similar. This is the end of the wafer here. So the dynamics or the shape of the potential through the sheath doesn't really tell us a lot. But the ion angular energy distribution starts to fill in. So this is this is just the ion angular distribution. You start seeing more population, more ions impacting towards 0 degrees here. And in fact, we now see more particles hitting right at 0 degrees. So the physics of that would be, obviously with certain collision momentum, with the momentum collisions, the collisions in which the particle total energy is conserved, but the momentum of the particle can change. You're pushing more particles than to hit at 0 degrees. That would be my interpretation of this. The ion energy distribution looks pretty similar. So little energy is lost due to the collisions, but I would just say keep in mind that the dominant collisional process just generally tends to be these elastic collisions. And so although that altered the momentum, you can also lose energy. The ions can lose energy to the neutral background. The total energy is conserved, of course, but the neutrals can pick up energy at a cost for the ions. So at higher neutral energies, I might expect to see more energy lost. So Robert asked, how many Debye lengths is the optimal focus ring height? I don't know the answer to that. I think a lot of this is trial and error, which is why you need simulations. So that would just be a question of setting up your simulations with some geometry in mind, and then just changing one thing at a time and running these simulations. I think I ran these on 6 cores. They took a couple of hours on 6 cores on a Windows machine. Overnight, just do 5 or 6 runs, or even more. You could set this up as a batch. It can help you do that so that one ends, another one starts, and then you come by the next morning and you've got 15 or 20 simulations to analyze. That's the nature of this sort of nonlinear modeling. But that's the power of it too. Okay, so sorry, Terry, I can't answer that specific question. So my job here is to show the power of this. I'd have to say it's a engineer, someone working in the silicon wafer industry's job to start answering those sorts of questions. So in this case, I was curious of what effect secondaries would have on this problem. And so, of course, we can answer that nicely with this post-processor that I wrote. My secondary model was pretty crude, I think. I would strongly suggest coming up with a better one, but this was just sort of a first stab at it to show that secondaries do have an effect. And so the secondary model would produce a secondary electron with a 30% probability. So that was just sort of my first stab at, okay, what can secondaries do? And this is the ion angular and energy. Well, this is actually just the ionic angular distribution. The black is a low focus ring with collisions, no secondary population. And I apologize, I'm partially colorblind. I choose colors based on contrast, but that doesn't necessarily mean I know what the color is. So the other color is with low focus ring with collisions with secondary electrons. And you can see that there is sort of this spike that leads to an asymmetry in the angular distribution. So, in the conclusion, I'm done now. I've done a lot of work on this, but not as much as could be done based on the questions that I didn't know the answer to. But there's certainly a lot of work that can be done. And I hope to have shown that the problem that I've set up is flexible enough to start addressing some of those questions. Even if I don't have them, I think that it's possible to get this tool into the right person who could answer some of those questions or other questions that they may have. And just as sort of a teaser, we will have in VSim-11 the ability to import your CAD and assign dielectrics to your pieces. Because we recognize that these geometries, these focus ring geometries can be very complex, and that to use the methods that we have been using to get the dielectric constants correct isn't feasible. So we were adding that in 11. At least that's for the electrostatic solve. It's always been there for the electromagnetic. And we are working on ICP. And we're hoping to make some good progress there, so that if a user wanted to, they could do the whole chamber in 2D. So we're doing it in 2D for now. So, and then Ashish, not sure how to pronounce. Yes, you can do this in a non-uniform grid. So that's a good question. You just couldn't do it in the visual setup. So we'd have to work with you to do it through a text-based approach. So that's the end of my talk.
Very good. Very good, Daniel. We've had a lot of questions. If anyone has any additional questions, you can type them into the Q&A. We've got some time before our next presentation starts today. I liked your answer though, Daniel. I mean, when you said you don't know the specifics, that's part of what we do here though, right? We're not experts on all of these manufacturing processes, but what we are is we're here to help people figure out for their own process, right? And so they can see what works the best for them. And I know this is something that you've worked on for quite a while. This and the corona discharge presentation you did yesterday have been some pretty big accomplishments for you in the last year. So it's been really good to see it all kind of come together.
Yeah, the analyzer in particular is a really great tool. I mean, this is an example, coming into this problem, of course, I don't know what tools are used in these specific industries. And the user comes to us and say, hey, this is a tool we use a lot and it's used a lot in industry. And we say, okay, well, we can write an analyzer and we can do that. And in this particular case, the data collection methods were already there. So for me, it was just a matter of writing the Python script, which I did relatively quick. and then getting it actually included in the software was the next step, because there are some more steps. As a software engineer, I'm not a software engineer, I'm a physicist. We have software engineers at TechX, of course, because we're a software development company. So it was a matter of working with people who are more at TechX, who could help me figure out how to do it correctly, the way all the other analyzers are done. So it was a bit of a process, but we got it included in VSim. So that, and so I'm just bringing that up because if you've got, if there's a tool that you use for looking at your data that's commonly done, you know, we can write an analyzer and make it easier for you to look at the data. And then, so Robert, finally a question I can answer. Yes, it will be as part of VSim-11, but if you want it now, I can send this to you now. Yep, and I can send you the analyzer, and I even have I've even written up the documentation that was part of the examples package. So I can send all that to you. Yep. If thermal velocity is very high, there could be negative injection velocities. I mean, okay, so if thermal velocity is very high, so I want to just point out that for these are typically low temperature plasmas, and so that's just based on sort of where the industry is at and what the industry is doing. So by low temperature, a few EV. So I'm just gonna put that out there because that's what this problem is meant to address. But let's just go ahead and address the rest of the question though. If thermal velocity is high, there could be negative injection towards I mean, right now we're absorbing particles at the boundaries. That's how we're handling the dielectric boundary. Some of those particles are absorbed, and they are what's called a they stick to the dielectric, because dielectrics aren't conductors. So if an electron hits some point on the surface, it'll tend to kind of hang out there. It's not going to migrate, especially over the time scale of the simulation. Over 1 RF cycle, most likely as many electrons as ions will impact it, and therefore it'll, over 1 RF cycle, it'll be charge neutral. Okay, so that's, and then the next, and then I had, for some of the simulations, I also had another population which were also absorbed, but then they could re-emit a secondary electron. So in essence, I am doing absorbing boundary conditions over at that left-hand side where the dielectrics are. It's just what happens once they're absorbed can differ depending on what physics you want to include. So.
Great questions, though, that we've been receiving. And, you know, I want to kind of point out Daniel, so he is one of our application engineers, and he is trained as a physicist. That's his background. And this is, you know, what he does is all of these problems, these two that he has featured during TWSS are problems that came to us from a client. And the client wanted to know how, you know, they have a problem they need to solve. And this is what Daniel does. He sits on it for a bit, and then he comes up with an approach that works for that specific problem. Because sometimes these things, you know, everything is unique and has different conditions that we need to take into consideration. And so this is something that he does with our clients throughout the process. They often come to us when they're trying out the software initially, and we work with them to make sure that we have a process to solve their problem or to model it. We work with them. And then at that point, once we know that we've figured it out and got a solution that will work for them, you know, that's kind of how the relationship with our application engineers works here. And I do think I have phenomenal application engineers here at TechX. They work really hard with our clients. So this is a great, you know, I love this, Daniel, because it is something that came from a client that you've worked hard and tweaked, and now it's ready to kind of show, you know, the world.
Yeah, and also keeping with that in mind, so when I work with clients, of course, I just want to be very clear that there is proprietary information, and that is never ever released. What I'll tend to do is say, hey, this sort of general problem is of interest to the community, based on inquiries and feedback that I get from going to conferences and just through email with these clients. And then I'll look for more generic problems to work to turn into an example. And so, for example, this wafer impact problem is pretty simplistic, and every company might have much more complex, very unique, very proprietary ways of handling that. And of course, I would never turn that into an example. But what I do is I look in the literature, I look in what's been published, and I'll turn that into an example. Because if it's in the literature and it's been published, then it's free to, it's free to use in the domain, so to speak.
It's a good clarification. So
yeah.
Exactly. Any additional questions do we have? Let's see. Oh, looks like we do. We have another one about our neutral species modeled as particles or fluid.
In this case, these particles were models of just a fluid background. You can put in fluids as particles, and then you can watch the evolution of the neutral fluid as well. The reason we're able to do that is because we use what's called a direct simulation Monte Carlo approach, which can model the evolution of the neutral species correctly also. But of course, that increases your computational cost because now you're following another set of particles. So if you don't really care about how the fluid's evolving, you know it's there, then you can use our fluid model. So I'll just show you how to do that real quick. If you go to the setup and you go to particle dynamics, there's a fluid tab here. But then under the kinetic particles, I can also add a neutral species as well. So you can do both. This particular one uses fluid. And it's the exact same set of collisions, I believe. They're pretty sure they're all the same collisions. It's just how it impacts the neutral that differs. Or how, I shouldn't say that. If you want to follow the fluid evolution, you do particle fluid or particle neutral. If you don't care about following the fluid evolution, you use fluid neutral.
Very good. And while we're waiting to see if we have any additional questions, I will say that if you have not tried out any of our software products before and you're interested in kind of seeing what our software can do, we have 3 different products: VSim, USim, and RSim. Daniel has been talking about VSim specifically, a multiphysics product, simulation product. And if you're interested in getting a trial evaluation so that you can see if this will work for you, you might even speak with Daniel, you can go to our website, which is www.txcorp.com, and there is a button there for receive trial evaluation. And if you put your information in, we can set you up with a 30-day trial evaluation of any of our software products that you want to consider. And we'll start with working with you that way. And then some of these documentations and examples are on our website as well. And it looks like we have another question from Bob Terry, which is, can you model charge exchange in the argon species?
Yes, you can. I just brought it up. It's just one of the many different reactions that can be included. The way you do that is, first of all, you have to go into basic settings and make sure that you turn on reactions here. So there's a collisions framework option. You click here. I always use reaction. Reactions came out. The reactions framework came out in VSim-9. And so ever since I've been at TechX, reactions framework has been there. It still uses the Monte Carlo approach, the direct simulation Monte Carlo, but it was sort of a separate branch off of what was originally there. Anyway, I always just do reactions for historical reasons. Some people may use other ones. And then once you include the reactions, you'll get this new tab here, which won't appear unless you include the reactions framework. And then expand. And then here you have particle-particle collisions, particle-fluid collisions. So if you right-click here, then you get that charge exchange option. So very, very, very nice. I've used other software where adding collisions was not so easy. So this was very easy, at least from my experience, easier.
Looks like we have another question about particle dynamics, asking about if the calculation is really relativistic.
This case, probably not. I would say you could go with the non-relativistic. I don't know. You probably would, since it's not computing gamma. I don't know how much of a speed up. I just default to relativistic. I don't really pay attention much, since that's always correct.